Hi everyone, and welcome to our fourth weekly webinar for the Udacity Deep Reinforcement Learning Nano degree. This week I'm going to follow on from last week's, looking at the Markov decision process, and then looking at the Monte Carlo method and the temporal difference method. And this week I'm going to focus on continuous control, discretization, talk a little bit about DRL, which will be coming next in the course, and I'll also be over the taxi example a little bit. So maybe have a look at the code and also at the 3.1 section of the paper, which you guys have reference to. So, like I said, basically we'll be going over the taxi example, which is in this document here, then go on to discrete continuous spaces, discretization, deep reinforcement learning, why deep RL, and deep RL and how do we do it, and sort of how do we train a deep RL compared to traditional reinforcement learning methods that use tabular format. So I hope you've all had a really good week going through the course content, and hopefully that this webinar will cover a few things and make things a bit more clear. And once again, if you have any questions at the end, there'll be a Q&A session, and also anything after you've looked at it, just have a look at the ask me any questions that you may have in chat or direct message me. So first, I'm going to, just get to the next slide. So first I'm going to talk about the taxi example, the environment, and the observation. So if you've had time to do the taxi project, great. Or if you've read through 3.1 section of the paper provided, I'm just going to basically break it down for you all, so you can sort of look at it in sections, a bit like we do with the problem itself. We break it down into subsections and tasks. So I'm just going to go through this, the same taxi environment that you'll be doing the taxi challenge with. So it's pretty much a 5x5 grid, as you can see there. There are 4 specifically designated locations, so red, green, blue, white, which is the yellow. The task is episodic, so it basically has a start and a finish, so it's not continuous or anything like that. Now, the taxi basically is that little, as you can see, symbol there, of course, and on the start of each episode, the taxi starts in a randomly chosen square. This makes it a bit more interesting because if it was in the same place every time, the challenge probably wouldn't be that difficult and we'd probably learn it quite quickly. But the fact that it's random gives it a bit more, makes it a bit more like real life. So basically, there's a passenger at one of the 4 locations, also chosen randomly, and that passenger wishes to be transported to one of the 4 locations, also chosen randomly. So there's a lot of random in this environment. Basically, the taxi must go to the passenger's location, the source, pick up the passenger, and then take it to the destination and put the passenger there. To keep things uniform, the taxi must pick up and drop off the passenger even if she is already located at the destination. Now, if this wasn't the case, it would probably wig out the program trying to learn. Now, the episode ends when the passenger is deposited at the destination location. So once it's picked it up, taken it there, dropped it off, it finishes, and then it starts another episode if you're doing multiple episodes. So the length of observation, or this state space, so if you're thinking about observation space or the state space which are actually provided, it's 25, the length of 25. So if it was an array, or at least it would be a one-dimensional with 25. This could also be multi-dimensional if you wanted to, but probably the simplest way is just that. It can be represented in many ways. Probably another thing to think about is how many discrete spaces there is. Because there's 25 taxi positions, 5 possible locations of the passenger, including the case when the passenger is the taxi, and 4 destination locations, there's basically 500 discrete states in there, which is not that much compared to some of the problems you'll be facing with deep reinforcement learning. But it's still a decent amount and requires multiple episodes to go to actually see all spaces, and having a good epsilon decay so you actually can see enough, but still trying to exploit it once you've learned. So next, I'm just going to break it down into different bits. So that was the observation. Now I'm going to look at the actions. So there is 6 discrete deterministic actions. So if this was a array of actions, you would basically, 0 could trigger move south, 1 move north. But basically, we look at them, these are the actions. So you've got move south, move north, move east, and move west. Now that would be sort of used for navigation. So that's for the thing to move around. So the actual taxi will move around. The other important 2 parts are pick up the passenger and drop off the passenger. So when it gets to the passenger, it needs to trigger the pick up passenger. So it grabs the passenger and puts it in the taxi, and then it would go and use those navigations to get to the drop off section, and then it would use the drop off passenger. So basically the number of actions are 6. And you'll see that in the taxi challenge code where it's got NA, which is 6, which is the number of actions. Now the other most important, well, not most important, but one of the main important sections, so you've got your state or observation space, you've now got your actions that you can do. Now the other most very important part of a reinforcement learning problem or a Markov decision process is the reward. So in this environment, there is a reward of -1 for each action, a reward of 20 for delivering the passenger, there's a good amount of reward, and there's a reward of -10 for executing actions, pick up or drop off illegally, which basically means if you put it in the wrong spot or pick it up or do the wrong of those actions, you get -10. So this will discourage the agent from doing this very quickly. So also, if a navigation action would cause the taxi to hit one of the walls, the action is a no-op. So there's only the usual reward of -1. Now you might wonder, why is there a reward of -1? Now, the reason -1 is very important for every action is if it wasn't there, the agent would get the +20 if it delivers the passenger, but it doesn't matter if it took 10 moves or steps or moves, or if it took 1,000,000, it would still get that 20. So we're trying to optimize the taxi to be as efficient as possible. So for every move, if it gets a -1, it forces it to do it quickly as possible. So if it's looking forward, it goes, well, if I do all these other actions, then I'm going to get -1, -1, -1, -1 again, and over and over. And so its expected accumulated reward will actually become less and less. Or sorry, it will have a less reward. And so what it's trying to do is do a short amount, very quick to get to the passenger, pick it up and take it to the spot. Now, as you know, the main goal of this example is to maximize the total reward per episode. So if it can find a way to pick up the passenger and take it there as quickly as possible, then it will maximize that reward. It will get that 20, but it will get less of a minus if it does it quicker. So once again, there's 500 possible states. There's 25 squares that it can actually go on. 5 locations for the passenger and 4 destinations. So sort of think about that a bit, before you look at the taxi challenge, and kind of just conceptualize the actual problem itself rather than just writing code or something that you don't know. And in the real world, what you're going to get is a problem. You're going to have to frame it as a markup decision process to a degree, and you're going to have to probably frame those rewards and that. So think about how the reward's been structured in this, because this has been already given to you, and how the actions and states make the problem bigger or smaller or harder or easier to work out. So the taxi example details, I'm just going to go into a bit more of the actual problem itself from the paper. So the task has a simple hierarchical structure in which there are 2 main subtasks. Get passenger, so that's getting the passenger, that's one sort of task that it needs to do, and the other is delivering the passenger. So they're 2 sort of separate things. Each of these subtasks in turn involves a subtask of navigating to one of the 4 locations and then performing a pickup or put down action. This task illustrates the need to support temporal abstraction, state abstraction, and subtask sharing, which I'll go into more detail. So, temporal abstraction. So the process of navigating to the passenger's location and picking up the passenger is temporally extended action that can take different numbers of steps to complete depending on the distance to the target. So, it may be different each time because of the randomness. It's not going to be identical every time. It will change. The passenger will be a different location. It will be in a different location when it starts to get to it. So, you have to think about that. The top level policy, get passenger and deliver passenger, can be expressed very simply if their temporal abstraction can be employed. Now, next, the state abstraction. So the need of state abstraction is probably less obvious. Consider the subtask of getting the passenger while the subtask is being solved. The destination of the passenger is completely irrelevant. It cannot affect any of the navigation or pickup decisions. So think about that. I'll finish off. So perhaps more importantly, when you navigate into the target location, either the source or destination location of the passenger, only the identity of the target location is important. But the fact that in some cases the taxi is carrying a passenger, in other cases it is irrelevant. So, for example, when it is looking at the state and its first task is to get the passenger, it doesn't really care at that point about dropping off the passenger yet. Its whole purpose is navigate to that passenger and then press the form the pickup action. And once that's complete, that subtask is finished. And then what it's doing is gets onto the next thing, which is then delivering that passenger to the next state. So part for subtask sharing is quite critical with this problem. So if the system could learn how to solve the navigation subtask once, the solution could be shared by both the get passenger and deliver passenger subtasks. So think about that. If it's in a spot and it goes and picks up the passenger and it navigates around, those same navigation could be used again if it was in that same spot when it picked it up to actually drop it off. This is used quite a fair bit, and I employ this think about this quite a lot when I'm forming actions. So, for example, financial data, financial markets is like that. So, if it performs, say, in a trade, and it's looking at, it buys and it's going in a particular way, it kind of can use that to know that if it gets a negative movement, per step, then it knows that the sell would probably do the opposite, or would do the opposite. So, you know, that is quite critical in the way agents, you know, look at the actual problem. Now, the other thing which we'll look at is, you know, constructing a max-Q decomposition. So the max-Q method provides a value function representation of the learning algorithm that supports the temporal abstraction, state abstraction, and subtask theory. So with this problem, we have to identify individual subtasks that we believe will be important. So, for example, navigation or navigate. In this subtask, the goal is to move the taxi around. So it's, you know, it's those four, you know, north, south, east, west, which moves the actual taxi from, you know, one state to the, or one part of the grid to the other. The other then would be get the actual passenger. So when it first starts off, it wants to get the passenger. So it basically, the goal is to move the taxi from a current location to the passenger's current location and pick up the passenger. And then the put, the goal of the subtask is to move the taxi from the current location to the passenger's destination location and drop off the passenger. And the root of, you know, task would be this whole process. So the taxi example primitive actions of the subtask. So, for example, the navigate or T subtask should use the four primitive actions north, south, east, west. The get subtask should use the navigate subtask and the pick up primitive action and so on. So the navigate basically uses that subtask and then it uses the pick up primitive action and so on. And then the put subtask should use the navigate subtask and drop off the primitive, use the drop off primitive action, and so on and so on. So you know, that gives you an idea of what's going on. So this is a graph of that. So you've got the root up the top. So for example, each node corresponds to a subtask or primitive action. Each edge corresponds to a potential way on which one subtask can be called, one of its child tasks. So as you can see, the root will either get the get or put, and it can either grab navigate, or it can use a pickup once it's, you know, got to the spot. So it's broken down into that, and within the navigate, you've got another, you know, 4 actions as well. So that's been split up. So, you know, think about this. So imagine trying to code this completely from scratch. So, you know, you're saying, if I'm in this location and blah, 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 sorry, in this location and get to this, imagine the code required to settle those actions. It just, you know, and this is not a really complex problem. Imagine that with like a game like Sonic the Hedgehog, and trying to think of every single state that character would be in. Or think of the game of chess or Go. You know, trying to code that from scratch would just be absolutely insane. And, you know, good luck to anyone that would even attempt to do that. So that's why we use, you know, agents, especially machine learning, and reinforcement learning is fantastic for these problems because of the way it optimizes the actions, you know, for the state. And so it can automate this process rather than having to think about every single thing. Now, I'm going to talk about the policy for the subtask. So we refer to the policy subtask as a subroutine. We can view the parent subroutine as invoking the child subroutine via ordinary subroutine call and return semantics. We have a policy for each subtask, then this gives us an overall policy for the taxi MVP. The root subtask executes its policy by calling subroutines that are policies for the get and put subtask, and the get policy calls subroutines for the pick up primitive action and the navigate subtask. We call this collection of policies a hierarchical policy. Hierarchical policies, each subroutine executes until it enters eternal state. Now, what we're going to do is we're going to use either a Monte Carlo or a temporal difference method to achieve this goals. and they do it really, really well. So what I'm going to do now is I'm just going to bring up some of the code. So I'm going to start off with looking at the taxi problem. So just quickly, briefly go over this before we go next, just to get you guys started. So, for example, environment gets kicked in by Jim, it gets created, so the taxi v2. The agent, which is very important, is taken from the agent.py, and basically it gets the average reward, best average reward, using the interact from monitor.py. So if we go to the agent, basically, as you can see, the number of actions are 6, like we said, and this is just the basics. So have a look through this code. Steps are extremely important because each step is doing an action, getting the next state and reward. And you can play around with alpha and gamma and try different algorithms. The monitor basically is going through. If you look through it, it's got epsilon, decay. You can play around with these and try all different things, higher, lower. I've been just mucking around a little bit with it. It's not purely optimized. It still gets the 9.28. But as you can see, there's basically a loop. So for episode in range, the number of episodes that we've set, it basically resets the environment, and then while true, it forms an action, gets the next state reward done, which is part of the Markov decision process. The agent step basically feeds in the state, action, reward, next state done, and then gets a sample reward, and if it's done, finishes it off, and basically and so on and so on. So a simple way, if you haven't played with it, it's python.main. Doesn't take very long to run. You'll probably find that each time it's slightly different because of the randomness. Sometimes it will perform better than others. As you can see, last time it was 9.2. This time, let's see what it gets to. Who knows? It's probably not going to do as well right this time. But, this is something that you play with, and you'll see that a lot with reinforcement learning problems. That's why we also use seed in the initialization of, for example, the weights and other things, but that still doesn't, the random environment, it can, especially in the real world, it will be different every time. So I'm going to go back to the presentation, and now we're going to, now that we've gone through that, I'm going to talk about discrete versus continuous spaces, or data, or whatever you want to call it. So a discrete data can only take particular values. There may potentially be an infinite number of those values, but each is distinct and there's no grey area in between. Discrete data can be numeric, like numbers or apples, but it also can be categorical, like red, blue, male, female, good, bad. But it's very specific. So while continuous data are not restricted to define separate values, but can occupy any value over a continuous range. Between any two continuous data values, there may be an infinite number of other continuous data, and always essentially numeric. So, for example, if a state was coordinates, that would be sort of almost, well, it's still sort of discrete to a degree, but basically, think about like arm joint movements of a robot. They might range between 0 degrees and 180, or it can do a full 360. Now that's continuous. It doesn't have a very distinct spot, but you're constantly moving it up and down, and it's between sort of a range. Discrete would be, for example, a button or a particular state. And typically what we do is we break down problems and try to make them more discrete because it makes it easier. And with traditional reinforcement learning, because of the state action, you want to sort of break this down into particular discrete states. Otherwise, the table that you're creating gets out of control, which I'll go into a bit further detail later. Discretization. It's converting a continuous space into a periodic space. How do we do this? We can use constant grid, style coding, course coding, and the advantages and disadvantages, which I'll go through. So the advantages is to make the problem simpler. It then gives you a finite amount of spaces to a degree, and allows you to use traditional RL algorithms. Now, the disadvantages is you're not getting the true state representation that can actually cause problems when it's learning and won't be able to optimize perfectly for what is really going on. So I'll go, so say you had a space that was almost continuous, you could just go around different points on say on a map. But typically what we do, for example, in the taxi, we break it down into a constant grid. And so it's got each individual state that it can go into. And if it needed to move around in a finite way, you would just have too many possible actions. Now, for example, so probably I'll go into the disadvantages. Yes, like I said, it will lose the proper state representation. But I'll go over just tile coding a bit. So instead of making a simple grid that covers the whole state space, like tile coding uses several overlapping grids, like layers, one over the other, and builds a feature vector. For instance, in an X, Y, Z coordinate case, so for example, if the taxi problem was X, Y coordinates, the tile could equal 1 if you are occupying that tile that it actually, or 0 otherwise. The feature vector is then used with parametric, e.g. linear or neural network approximation of the value function. From this point of view, the tile feature vector is very high dimensional, sparse representation of a low dimensional dense coordinate system. So it's basically breaking it down and making it simpler. Combining high-dimensional representation could capture the structure of the state transition kernel and reward function. So that can lead to good approximation of the true value function, somehow like kernel methods, which I won't go into. Now, this is constant grid, and this is tile coding, so you can actually see this. And this is other forms that can be irregular, log stripes, and diagonal stripes. So these are different forms of tile coding. I'm going to go just briefly into course coding. These are just some different representative course coding, but you've already gone over this in the course, so I'm not going to cover it in any more detail. Now, so I'm just going to start now. As you're finishing up your introduction to deep reinforcement learning, you've been mainly learning about traditional reinforcement learning methods. And so the next stage of this is to go to deep reinforcement learning. And I'm going to explain why deep reinforcement learning is important in reinforcement learning and why it has such amazing benefits. So I'm just going to go over Q-learning again. So Q-learning estimates the state action value function, QSA, for the target policy that's deterministically selects the action of highest value. Now this is put into a Q table, which is the size of state times action. Now to calculate the current state action value, it takes the next best action from the table Q, max A, Q, next state action. And let's say that we had a problem with a total of 4 different actions and 10 different states. Then we've got a Q of 10 times 4. Now, it works perfectly fine if we have a limited state space action, but when the state space is much bigger. Now, a simple one would be go. chess. So Go has 10 to the, 160, 180 possible, so pretty much more possible states than just about all of the known, stars or atoms in the universe. It's almost infinite. So we're pretty much not going to be able to create a Q table and put that in memory on modern PCs. We just can't do it. So we won't be able to actually have a table with all of those state action pairs. So what do? This limits, traditional methods like Monte Carlo and TD struggle with this, or Q learning. How do we get around this? Some clever people came up with some cool ideas. And what it was doing was adding the deep to RL. So once again, if you look at representation on the side, that's a deep reinforcement learning. A reinforcement learning problem using a neural network or a deep neural network to construct the policy. So Q learning function, see below. Now, what would happen if we used function approximation, e.g. a neural network, to calculate these Q values? That's where deep reinforcement learning comes in. So this is how a neural network Q function works. I'm just going to break it down. I'm not going to go into code specifically, but just to give you a more of a high-level understanding of what's going on. So the network takes a state as the input and produces a Q value for every action in the action space. None of the actions depend on the game environment. The neural network's job is to learn the parameters. So assume that the training is done and we've got the final network ready. So think that we've already done the training. I'll talk about the training next. At the time of prediction, we use the trained network to predict the next best action to take in the environment. So we give an input state, the network gives the Q values for all actions. Then we take the max Q value to take the corresponding action in the environment. So the best action is an argmax max of the neural network Q values. This is, if you've done deep learning, you understand this. So, for example, object recognition would give you Q values of objects that it's recognized, and then give you, the Q values for that. Won't give the Q values, but gives you the predicted values. In this, what it's doing, instead of having a table that it's looking at for these Q values, it's using a neural network. Now, this means that we can almost have a infinitely bigger action space and state space that we can use. So this works great for continuous control problems. So, if it is a range between 1 and 1,000 that, is the actions, or it's multiple different joints and actions, and the possibilities is almost infinite. So a neural network will work great, especially also in chess, for example, where there's, more possible states and, all the atoms in the universe. So basically, the best action to take in the environment is the argmax of the neural network predicted Q values. And as you can see here, state action network Q values from the state network. Hopefully this makes a bit more sense, but you'll go into more of this once you go into the value functions in the next part and actually go through a deep Q network. But there was a few problems with this, and doesn't train very well, so they had to implement some tricks, which you will learn about in the next part of the course. I'm going to go into just the basics of how you will train a neural network for Q values. So it's a regression problem, so we use a regression loss function to minimize the total error of the training data. A neural network loss function for predicting the Q values, so L2 loss predicted, as you can see. Just assume that the predicted gives the list of action values from a neural network where we take the maximum value, maximum reward. Since we don't know the actual, as it's a reinforcement learning, not supervised, so we don't have labels. So we have to estimate the actual value. So actual is R plus gamma max, next action and next state action. So basically, break that down again. R is the current immediate reward. S is the next state, and then you've got the max next action state pair from the Q values. And of course, gamma is the discount factor. Hopefully that gives you a bit of a breakdown of what's going on. It's not too much different to what you've been learning. It's just adding in a neural network instead of the table. Now, the reason for this, if you take that particular action, you'll know the reward and predict the next match reward within the sum discount. Assuming the next match reward predicted by the model is completely wrong. So it's just completely got it wrong. And it's just started chaining. We'll still get a reward back. That is 100% right. That doesn't change. So slowly we adjust the network's parameters to predict a reasonable prediction. In a sense, it predicts its own actual values, but since R is not biased, when we step into the environment, we observe the reward, which is fully right. The network is going to update its gradients using back propagation to converge. We then get the inputs, labels, reward, loss function, and we can build a neural network which predicts the Q values for every action value, which means for this state, there is actual values for each action. Now, hopefully, that makes a bit of sense. So pretty much, if you just want to break it down to some simple ideas, deep reinforcement learning equals deep learning plus reinforcement learning. Deep learning, it's basically deep learning with no labels, and it's reinforcement learning with no tables. So you can see that it gives us a huge opportunity to do incredible results, and that's what we've seen. The advances that DeepMind and OpenAI and a lot of the different research have come out with has allowed us to tackle problems which probably were thought to be unachievable before with traditional methods, or we just didn't have the computational space to deal with them. Neural networks get around this, and we've found some really good ways to apply these to this problem. So I hope this has sort of given you a few ideas of where you're going to go to next in the course, and the next part of the course is really cool. You get to learn about deep Q networks, you get to learn about and then after that you learn about policy-based methods, and then we learn about multi-agent, so combining multiple agents. So from traditional methods to what we can achieve now, it's incredible. And the algorithms like soft actor critic, which has come out recently for continuous control task, it's just unbelievably good at what it can do compared to some of the earlier algorithms that first came out. And most of the early algorithms were still discrete in reinforcement learning, especially for the actions. So we've now gone into a new sort of world of deep reinforcement learning, and the sky is the absolute limit. So here's a couple of my references. Paper and also a bit of Medium posts. So now I'm going to just have a bit of a Q&A time. I'm just going to give you guys a couple of minutes to ask any questions and just post them in the chat in YouTube, and I'll just wait to see if we have any of them. No one has any questions at the time, so that's fine. Look, if you have any questions afterwards, DM, put it in the channel, whatever you like. So you may have time to process it, and if you watching this recorded, you'll probably have questions later on. So what I'm just going to go over before I finish up this session is what I'm going to go over next week. So next week, even though you've just started on you'll be starting potentially on the value-based methods, I'm going to go over the navigation project, so your first major project, so you've got a bit of an idea and it's in the back of your head for as you're studying the DQ network and going through the course. So I'm going to go through the base code that is given. I'm going to talk about setting up in different environments. So either use the workspace, or if you want to do it on your local PC, or if you want to do it on AWS. I'm just going to go and talk about how to set that up. I'm going to go through probably the code itself and try to explain each section of it, just to get you all started and explain what's going on, and give you some hints and tips of what to do and how to start. A lot of that's in the guide for the actual project. Sometimes it's good to clarify and go and have someone to explain it in more detail. The other thing that I'll probably do is give you some extra reference material to have a look at. You can look through the examples for the DQ networks. What I suggest, and one of the things I'll go over, is push yourself. Get the project done early, expand it, add extra features, add, say, prioritize experience replay. Try to apply all the techniques that you've learned, and maybe apply ones that you've researched yourself. It shows that you understand and how to implement it. So, that's pretty much all for today. And I hope you're all looking forward to the next part of the course. And we're going to get into some really cool material. The DeepQ network was the first deep reinforcement learning algorithm that I played with before I started studying, and I just loved it. It was a basic version of DeepQ network in Keras, and I constructed my own environment and got it to learn from it. And didn't really understand it until I started learning reinforcement learning itself. But what I found is it gave me the appetite to look at all the other algorithms. It's quite probably simple in a degree to some. Proximal policy optimization in policy gradient methods is pretty simple and cool and works really easy. But this is now you're getting into the real exciting part of this course, and probably what a lot of you wanted to get into from the beginning, which is deep reinforcement learning. So once again, thank you very much for this webinar. Next week we're going to go into some details of, and I might even have time to go through the DQ network, or even just go through other parts of the optional material that you've got. For example, deep RL for robotics, or neural networks and convolutional networks. I might put a bit of a question out there to what you guys would want to look at, rather we go more into the project itself. Well, once again, thank you very much, and have a fantastic week looking at the material, and good luck, and see ya.